The observable universe appears far too uniform for regions that may never have had enough time to exchange information. Current inflation models suggest space expanded so rapidly that light itself could not keep up with the separation. The cosmic inflation field is proposed as a mechanism that briefly dominated the earliest state of the universe. Instead of matter moving through space, the structure of space itself may have expanded exponentially within an extremely short interval. If that expansion occurred quickly enough, regions now separated by billions of light years could have originated from a much smaller connected state. The inflationary imprint observed in large-scale cosmic structure may preserve traces of that expansion. Without inflation, early regions of the universe should have evolved independently once separated beyond causal contact. Small differences in energy density should have amplified into major irregularities across the observable universe. Instead, observations of the cosmic background appear unusually smooth across immense distances. Temperature variations exist, but they remain remarkably small compared to what unconstrained expansion models would predict. That apparent smoothness creates the central contradiction. The universe appears coordinated on scales where no coordinating signal should have been physically possible. One explanation proposes that inflation stretched a tiny uniform quantum region into the entire observable universe. In this view, rapid expansion preserved early uniformity before ordinary relativistic limits became dominant again. The inflationary field in this framework behaves like a temporary energy state embedded into spacetime itself. Its energy density may have remained nearly constant even while the volume of space increased dramatically. As space expanded, tiny quantum fluctuations inside the field could also have been stretched outward. Those microscopic irregularities may later have become the seeds of galaxies and large-scale structure. This creates an unusual dual effect. Inflation appears capable of explaining both the extreme smoothness of the universe and the existence of the small variations required for structure formation. But competing models interpret the same observations differently. Some theories propose that inflation was driven by a scalar field with specific energy behavior, while others suggest multiple inflation phases or entirely different expansion dynamics. Certain versions of inflation predict measurable gravitational signatures embedded into primordial radiation patterns. Yet current observations have not confirmed those signatures conclusively. That absence does not eliminate inflation, but it weakens some versions of the theory. The mechanism may still explain the observable pattern while remaining physically incomplete. Other competing models attempt to avoid inflation entirely by modifying early universe geometry or proposing alternative causal structures. These models try to reproduce large-scale uniformity without requiring faster-than-light expansion of spacetime. The difficulty is that many alternatives reproduce only parts of the observed data. They may explain smoothness while failing to account for fluctuation distributions preserved in cosmic structure. Inflation itself also introduces unresolved boundaries. The field responsible for expansion has never been directly observed, and its physical origin remains uncertain. Current models describe how inflation behaves mathematically, but not what generated the inflationary state initially. The mechanism appears effective observationally while remaining physically detached from known particle systems. This creates a deeper mismatch between prediction and explanation. The theory may successfully reproduce observable structure while leaving the underlying driver fundamentally unidentified. The scale involved intensifies the uncertainty. Inflation may have expanded the universe by incomprehensible factors within fractions of a second, pushing ordinary physical intuition beyond usefulness. At those scales, even conventional ideas of distance and causal separation begin to lose intuitive meaning. Space itself becomes the evolving system rather than the stage where events occur. The observable inflationary imprint may therefore preserve information from a phase where known physical behavior operated under radically different conditions. Yet that phase remains inaccessible to direct observation. Some models predict that inflation never fully stopped everywhere. In those scenarios, isolated regions of space-time could continue expanding independently beyond observable boundaries. That possibility creates another unresolved consequence. The observable universe may represent only one localized outcome of a much larger inflationary structure. Even if inflation correctly explains the large-scale uniformity problem, the theory does not fully explain why inflation began, why it ended, or why its energy behavior produced this specific cosmic structure. The observable pattern appears physically real, but the mechanism behind it remains partially hidden behind the earliest unreachable moments of cosmic history. What remains visible today may only be the stretched aftermath of a process that current physics can model mathematically without fully understanding physically. If inflation expanded space faster than causal signals could propagate, then the observable universe inherited structure from a phase no longer physically accessible. The visible pattern survives, but the originating conditions remain hidden behind the expansion itself. The inflationary imprint appears across immense cosmic scales. Slight variations in density repeat statistically across regions so distant that ordinary interaction histories become difficult to reconstruct cleanly. Those fluctuations were extremely small at the beginning. Over billions of years, gravity amplified them into galaxies, clusters, and large-scale cosmic filaments. That amplification creates a strange dependency. The largest structures in the universe may ultimately trace back to microscopic irregularities stretched during an almost unobservable phase. Current measurements rely heavily on relic radiation patterns preserved from the early universe, but those signals have propagated through expanding spacetime for billions of years before reaching detectors. Every stage of that propagation introduces uncertainty. Later cosmic evolution can distort, obscure, or statistically imitate parts of the original inflationary signal. Some predicted inflation signatures are also so weak that they approach the limits of observational precision. The deeper the model reaches toward the earliest expansion stage, the harder direct verification becomes. This creates a tightening boundary condition. The mechanism may only leave indirect evidence while remaining permanently beyond direct measurement. Competing inflation models often produce nearly identical large-scale observational outcomes. Different physical assumptions can generate similar imprint distributions across cosmic background structure. That overlap creates analytical tension inside the theory itself. Observations may support inflation broadly, while failing to isolate which inflation mechanism, if any, actually operated. Some versions require inflation to stop uniformly across spacetime. Others suggest localized termination, where separate regions evolve differently depending on field behavior during expansion. If those differences existed, most of them would now lie beyond observable reach. Expansion itself may have separated entire regions permanently faster than information could reconnect them. The anomaly therefore expands beyond early uniformity alone. Inflation may not only explain the observable universe, but also imply unreachable structure outside it. At extreme scales, ordinary geometric intuition weakens further. Distances that appear causally disconnected today may once have occupied nearly identical physical states before rapid expansion stretched them apart. The observable pattern still reflects that earlier connection, but the original configuration cannot be reconstructed directly because the expansion erased much of the accessible causal history. Some inflation models also depend on highly specific energy conditions remaining stable during expansion. Small instabilities inside the field could dramatically alter the resulting cosmic structure. Yet the observed universe appears unusually balanced. The expansion seems to have ended within a narrow range that allowed matter to organize without collapsing immediately back into disorder. That apparent balance sharpens the unresolved dependency. Inflation may require conditions that current physics can describe mathematically, but cannot explain naturally. The deeper the models extend toward the beginning of inflation, the more conventional physical frameworks begin merging with quantum uncertainty. Known descriptions of space-time become increasingly incomplete under those conditions. Observable structure remains clear long after the underlying mechanism disappears from direct access. The universe preserves the aftermath while concealing the process itself. Even the timeline of inflation remains uncertain. Current models estimate an extraordinarily brief expansion interval, but the exact duration changes the predicted structure distribution across the observable universe. A slightly different expansion rate could have produced radically different cosmic organization. Small parameter shifts propagate outward into universal-scale consequences. That propagation effect remains one of inflation's most unsettling implications. Tiny early-state variations may determine the structure of everything visible billions of years later. The observable universe therefore behaves like a stretched record of an inaccessible event. The larger the cosmic scale becomes, the more the original mechanism retreats beyond direct physical reach. Inflation explains why the observable universe appears smooth across distances that should never have shared information under ordinary expansion. It also explains how microscopic fluctuations could propagate outward into the structure of galaxies and cosmic matter distribution visible today. But the explanation remains incomplete at the point where the mechanism itself must be defined. Current models can describe how inflation behaves once assumed, yet they still cannot determine what generated the inflationary field or why its expansion state began at all. The observable imprint survives, but the initiating condition does not. Expansion may have permanently separated the physical origin of the process from every region now accessible to observation. Some inflation models remain mathematically consistent while predicting regions of space-time that can never be measured directly. Other models avoid inflation entirely, but fail to reproduce the same large-scale structure cleanly. The contradiction remains physically intact. The universe appears coordinated beyond ordinary causal limits, and current physics still cannot fully explain why.